So one of the questions was asked regarding the time interleaving. So I don't know which one of you had asked me, but the question is the following. So let's say you have 2x time interleaved ADC. So as we saw, the idea is, let me draw it here. So let's say you have a master clock like this. Okay, so the falling edges, as we saw, determine the sampling time instance, right? So let's say this is some 0, this is TS, 2TS, 3TS, and so on, right? And let's say this is my continuous time signal. Okay, so ideally, what you want to take samples of this signal at these time instance, right? So at TS, 2TS, and so on. Okay, and this was achieved in an interleaved fashion by having two ADCs, right? The first ADC was sampling at, say, these points, 0, 2TS, and 4TS. And the other ADC was sampling at these points. So I'll mark them with cross, right? TS, 3TS, and so on. And you kind of switch between the two ADC outputs to realize the full rate ADC, right? And so if you look at the clocks that are given to the two ADCs, how will they look like? So these should be the sampling instance for the first ADC. So the clock should have something like this. Oops. Okay. Yeah. So for the first ADC, that is sampling at these time instance, which is 0, 2TS, and 4TS, right? The clock must look something like this, right? So the falling edges again define the sampling instant. And for the second ADC, the clock will just be phase shifted version of this. Okay. So here these define the sampling instance, and this is how it works. And one of the non-idealities we saw was that there could be an offset between the two clocks. That is, in principle, you want the falling edges of these two clocks should be offset by TS. But in practice, because of the way you generate these clocks, or due to some mismatch in the way you are actually routing the clock signals, there can be some timing offset, right? And one of the ways in which this timing offset could be addressed, what was it? How can you address this timing offset issue? Yeah, so one was to correct it digitally by changing the phases of the clock. And before that, I had mentioned that you can also have a sample and hold, right, operating at the full speed of Fs. And this is then given to the two ADCs, right? And how will this help? Well, let's say you this signal is continuous time signal is given to the sample and hold. How will the output of the sample and hold look like? So at this point, the input is sample, it will be held, right? And the next sample is here. That will, so the next sample will be held like this, right? It will do something like this. So, right? So now, even if there is some offset in the or delays in the sampling clocks like this, okay. So what will happen now? The entire the signal at during this entire time period is equal to the signal that you are sampled at this time instant, right? And these time instants are well defined by your master clock. Okay. So even if there is any change in the or any delays in the sampling clocks, that is delays of these two clocks. So instead of sampling at this point, that is this clock, say it samples with a slight offset here, it is still okay because you're essentially sampling at this instant, and the signal at this instant is same as this guy, right? Is that clear? Similarly, I mean, same holds good for this also. Even if there is a delay in this clock, you will be sampling at say one of these time points, right? But the signal value at this time or during this entire period is equal to the signal you had sampled at this TS. Okay. So as long as this clock has well-defined sampling instance, which of course you wanted, because even if you want to have a full rate ADC, you want to have a good clock to sample the signal, right? So let's say this is a given. So as long as this sampling edges are defined properly, there will be no offset issue. That is no issues due to this timing skew. Okay. So the question is this following. So what I mentioned was the sample and hold needs to be operated at the full speed FS. And I mentioned in some cases it might not be possible to realize this high speed sample and hold. So in that case, we resort to this digital calibration where you have right. Correct.
There will be another error related to the separate because it is just taking an average value of that signal for particular dimension, not average, a fixed value for a particular dimension. So, in order to remove one option here,
no. So, okay. See, remember, if for a sample and hold, if you want, I mean, this is the simplest sample and hold you can have, right? Right. So, ideally, what should be the resistance of the switch? I mean, okay, ideally, what do you want that R on to be? 0, right? So if you have a 0 on resistance, will there be any averaging at all? I mean, the point is if you have an RC circuit, if the RC time product is large, then the signal gets averaged, right? If the resistance is 0, you essentially have the signal connected to a capacitor. So capacitor voltage is going to follow the signal, right? That's all.
So what I want to mean is that when we are converting this by sample and hold, when we are converting this analog signal to a digital form,
right?
There will be a quantization bias, right?
Yeah, I mean that is something we cannot avoid, right? I mean,
in order to remove that offset error, we are using offset error. We are getting
no. Okay. Hold on. Let me stop you there. We are not trying to avoid the offset or the error that is added by the quantization process. Yeah, but that is something you cannot avoid, right? I mean, you have an ADC. Let's say you want a 6-bit ADC. It is given that there is going to be some error, right? Only if the ADC has infinite bits of resolution, you will not have any error, isn't it?
In order to remove the offset error, we are getting this quantization error. So is the value of quantization error less than the offset error?
Okay, hold on. See, the idea of interleaved ADC is this. So I want to realize an ADC, say it can be a 10-bit ADC, okay, operating at a sampling rate of FS. I find that I'm not able to, I'm able to design the ADC, but I find that I'm not able to operate the ADC at this full speed FS. Okay, so what I do, I find that the ADC works perfectly, say at FS by 2. But my original goal was to design an ADC, the same 10-bit ADC, running at FS. Okay, so that is why what I do, I have one more copy of this, the same ADC, running at FS by 2. Okay, so this will be sampling at say 0, 2 TS, 4 TS, and so on. This will be TS, 3 TS, 5 TS, and so on. And then you switch between these two outputs. That's the point. Okay, so where is the quantization error you were saying now?
I'm seeing that there is an offset error. There can be an offset error between 2 and 1 reduces.
No, okay. I am not talking about the offset mismatch in the offset error. This is regarding the error in the timing skew. If you remember, hopefully we have it here. See, so one was this offset error, and the only way to correct for it is to add an additional offset at the output here, right? That is one. The second is again gain error mismatch that you tackle by having a digital gain at the output that can correct for this gain error. Okay. The third error, which is what I am discussing now, is this timing skew or offset in this clock's sampling instance. So this is what I'm talking about. So let us say this first clock is fine. The second clock has falling edges, with an offset of delta t. So this is what we are talking about. Okay.
So we want to reduce due to this mismatch in delta t.
Right.
We want to reduce the error that we get. Right.
We want to completely eliminate in principle. Yeah.
So, but what I'm saying is, in order to eliminate this error,
okay,
we are using sample and hold circuit.
Okay.
That itself has some quantization errors
No.
associated with it.
No, why do you think sample and hold has a quantization error?
Because for given range of analog signal, we are streaming into a certain
No, no. No. See, we have two operations, right? One is sampling and one is quantization, isn't it? Sampling is just what it does. We have a continuous time signal. Let me draw it here. Yeah, we have a continuous time signal like this. I'm going to take the signal at this point. That's all. Okay. I'm just sampling the signal at this point. The voltage is still the same. If this was, say, some 100 millivolts or 101 millivolts, even this entire thing will be 101 millivolts. Only after doing this sampling, we do the quantization, right? That's where you are introducing error, right? Clear, right? Okay, so let me get back to the question. So the question that was asked was this. So as I mentioned, if you have a sample and hold operating at the full speed, then you can eliminate the error that can arise due to this timing skew. Okay, and it is possible that in many cases you might not be able to realize the sample and hold operating at the full speed. And in these cases, we resort to digital calibration where you have multiple phases of the clock and you use the appropriate phase to make sure that the timing skew is cancelled. But the question was, well, if you can interleave the ADCs like this, I mean, the original point was we are not able to operate the ADC at the full speed. So we took two different ADCs operating at half the speed and interleaving it, right? So the question was, why can't we do the same thing with the sample and hold also? That is, why don't I have the sample and hold also operating at the half rate? Okay. And then you give it to the ADC. Seems like a reasonable question, right? So any comments? Correct. I mean, that's what we want for this ADC, right? Each of these ADCs are sampling at half the sampling rate. So the sampling period for these ADCs is 2 TS, right?
I think if I reduce the sampling frequency, then I have to increase the time period. So RC value will increase, CU will increase, so area will increase.
Yeah, I mean, that's good, right? The question is this fine, or do you think there could be some issues with this? Right? Okay. Fine, right? I mean, so what he's saying is this. So let me just copy paste this. So let me just erase this format. So if you have to interleave that sample and hold also, what you need, so let me draw that here. Two sample and holds, right? We need to generate the clocks for these two sample and holds, right? And it is possible that in the process of generating these two clocks, we can have this offset error, that is this timing skew. Okay. So even though even though you interleave the sample and holds, the process of generating these two clocks from this main clock can potentially introduce this timing skew. So if the continuous time signal is doing something like this, so let us say when you try to generate the clocks from the main clock, it turns out that you generate it like this. Okay, say with some error. So now instead of sampling at this point, the first ADC, that is this guy, it will sample the signal at this time instant, right? Similarly, this guy will sample at this time instant. And this spacing need not be equal to TS. That's the idea. Okay. Is that clear? I forgot which one of you had asked me, but yeah, hopefully this clears it. Okay, so it is, I mean, although in principle it is possible to have an interleaved sample and hold, even when you interleave the sample and hold, you'll have the same problem. So the only solution to this is to make sure that you have multiple delayed versions of the clock and choose one of the versions or one of the phases of the clock so that the timing skew is minimized. That's all you can do. Okay, so that let's get on to the pipeline ADC we were discussing. Yeah, so in the last class we looked at the pipeline ADC operation, where here we have taken a 3-stage ADC. So the idea was you have the first ADC, whatever error the first ADC introduced, you find that error by subtracting the input and the output of the ADC, amplify that error, give it to one more ADC, right? And you can do it in multiple steps. And overall, you find that when you do it properly, the quantization error or any error that is added by the first, the initial ADCs, they get completely cancelled. And you end up only with the quantization noise of the third ADC or the final ADC. And that gets divided by the overall gain it sees before. In this case, 2 gains, G1, G2, right? And to make sure that this ADC has, and you make sure that there is no, we are utilizing the, we are not compromising on the sampling rate. What we do was we pipeline this entire operation, that is, we run all the ADCs concurrently, right? So when the first ADC is processing the first ADC say it's processing the third input, you make sure the second ADC is looking at the second input and so on. So this way, at each clock cycle, you get an estimate of the input. So you don't compromise on the sampling rate, but you can increase the overall resolution. That's the idea, right? And here we saw that in principle, if this was a ADC with B1 bits of resolution, the gain that we have to use for this residue amplifier ideally is 2 power B1. And similarly for this ADC, if it's B2 bits, it's 2 power B2 here. So overall, when the quantization noise gets divided by the product of these 2 gains, it turns out that this corresponds to an ADC with B1 plus B2 plus B3 bits of resolution. And the way to combine the 3 ADC outputs is also trivial in this case. All you just have to do is concatenate the 3 ADC outputs, right? So this is the ideal operation. But of course, in practice, you will have a lot of non-idealities. And the only 3 blocks that are here are the ADC here, the DAC, and this amplification operation. So we started to look at the non-idealities. So first we looked at the non-ideality that can arise due to this ADC. And whatever non-ideality that can arise can be, whatever non-ideality that is associated with the ADC comes because of the fact that the transition voltages can be having some kind of error. So for example, instead of having the transition voltage here, this can be at this point, right? And if we have some error like this, what we saw was the quantization error. Ideally, it should have been within plus or minus VREF by 4 in this 2-bit ADC. It turns out that it can grow beyond this range. So when you use a gain of 4, which is what you would want for a 2-bit ADC, because the gain is 2 power 2, you found that the gain times quantization noise can exceed the reference voltages, right? And this will in turn overload the succeeding ADCs. And the solution to this problem was simple. What we do was we choose a gain that is smaller than 2 power 2 or 2 power B1 in general. And of course, one choice was to use a gain of 3 in this case. And we saw that if you use a gain of 3, this digital operation becomes slightly tricky, right? So the usual choice is to have a gain which is a power of 2. So that's because the digital operation is simplified because division and multiplication by powers of 2 is straightforward. So we choose a gain that is a power of 2. And of course, we saw that the gain has to be less than 2 power 2. So in general, we choose a gain of this form. That is, if the front-end ADC has B1 bits of resolution, you choose a gain which is 2 power B1 minus 1, right? And the moment you do that, you find that the quantization noise here can exceed slightly greater than 1/4, that is Vref by 4. So instead of using a gain of 4, if you use a gain of 2, the quantization noise will be within this range, minus Vref by 2 to plus Vref by 2. And even if the quantization noise exceeds Vref by 4, this might only exceed slightly beyond minus Vref by 2 and plus Vref by 2. That's fine, right? Ideally, it's within plus or minus Vref by 4. So if you use a gain of 2, it's going to lie in this range. But because of some error, it can go slightly beyond Vref by 4, right? And if it goes slightly beyond Vref by 4, this might also slightly go beyond plus or minus Vref by 2. But that is still okay because it is well within our limits of plus or minus Vref, right? And of course, when we do this, say we have a 2 and 3 bit ADC like this. Yeah. So the gain we use here is 2. And we found that the overall resolution of this is only 4 bits. Although in principle, with a 2 bit and a 3 bit ADC, we can get an ADC with a resolution of 5 bits. Okay. So again, when you combine the two ADC outputs, there will be 1 bit of overlap. So earlier you saw that you can just simply concatenate the ADC outputs. But here, since you have a gain that is less than 2 power B1, when you combine the digital outputs, there will be 1 bit of overlap here. So essentially, you need an adder. Okay. And the output of this addition operation can in turn have 5 bits. But it can have only 16 possible output ports. Okay. So although we have 5 bits equivalent, we will not have all 32 output codes, right? Because with 5 bits, you can have 2 power 5 codes, 32. But since the overall resolution we have is only 4 bits, you'll find that we'll not have all 32 codes, but only 16 output codes. Okay. And here again, there was one question. So let me address that. So let us say there was no error in the transition voltage. So the quantization error will be bounded between plus or minus Vref by 4, right? So when you use a gain of 2, gain times quantization noise is within this range. Okay. So the input to the ADC is going to lie in this range, right? So you will not have any of these codes here, right? So only half of the codes here will be appearing at the output. And that is why we saw that instead of having 32 codes, you just have 16 codes at the output. We'll have only exactly 16 actually. Yeah. This can expand beyond. Yeah, that is correct. So this is a case ideally where when there is no error, you have the quantization noise bounded between plus or minus Vref by 4. But if there is some error, this can go slightly beyond, right? So when you amplify this by a factor of 2, this will slightly exceed, say, plus or minus Vref by 2 like this. Okay. Yeah, we can have more than 16 possible codes, but when you find the SNR of the ADC, it will be equivalent to a 4-bit ADC only. Yes. No, MSB is not this one you are saying. You cannot say this is a redundant bit. That's what I'm trying to get. So you have 5 bits here, but this entire 5 bits represent a 4-bit output. That's the idea. We cannot say which one of these is a redundant bit, right? Because if you remove this just 0 0 something, right? You are losing this. You need all the 5 bits, but at the output, if you compute the SNR, you'll find that it corresponds to only a 4-bit resolution. right? Again, in principle, if there was no error, you will find only 16 ports. But as he mentioned, when you have this error, the quantization noise can grow beyond plus or minus VREF by 4. So when you have a gain of 2, the quantization noise, I mean the amplified quantization noise, can exceed this range of plus or minus VREF by 2, right? In that case, you can find that even these codes will be exercised, some of these codes, okay? But overall, the resolution is of only 4 bits. So I know this might not be very intuitive, but I think you just have to get your heads over it. That's all. There is. Is that fine? Okay. And the kind of no, the point is the quantization error you make finally still it will be within this bound. That is, you have Q2 by 2. Right? I mean, in fact, you'll find it might be slightly less than 4 bits in some cases also, but roughly it will be 4 bits. I mean, the resolution is finally determined by this guy. The quantization noise of the last ADC and the gain you use. Okay. The quantization noise added by this first ADC is of no use because that completely gets cancelled. So the overall resolution is determined only by the last stage and the gains you are using in the previous stages. That's all. Okay. So of course, this was called redundancy because you're having 5 bits, but although your output is of only 4 bits of precision. So the extra bit is a redundant bit, and that is added to account for these kind of errors. That's all. And when we try to expand it to a single bit quantizer, which has only 2 levels, we saw that following our principle, we have to choose a gain of 1. And of course, that doesn't bias anything. So the minimum gain has to be 2, right? But for a minimum gain of 2, we have only 2 levels. The quantization noise can go beyond VREF by 2. So if you use a gain of 2, the amplified quantization noise can exceed the range. So what we did was, instead of having only 2 levels, we introduced one additional level. Okay, so for a single bit quantizer, which has only 2 levels, the quantization noise ideally is within this range, right? Okay, and we saw that the minimum gain you want to use is 2, right? So in principle, G times Q will be within the limit, right? But if there is an error in this threshold, the quantization noise can exceed VREF by 2. I mean, you can see here, right? So at this point, the output is VREF by 2, but the input is, output is here, right? Output is minus VREF by 2, this guy, but the input is some positive value, right? So some positive value minus VREF by 2, it's going to be beyond VREF by 2. So if we have a gain of 2, that's going to go beyond VREF. It will go beyond plus or minus VREF. You want to avoid it, right? So one thing is clear, the minimum gain has to be 2. But if the minimum gain is 2, you cannot have a 2-level quantizer. Okay, and that is why what we did was we introduced an additional level. So we have a 3-level quantizer like this, right? And it made sense to have the 3rd level within this range, minus 1/4 to plus 1/4. Okay, so let me once again explain this clearly because I think there was some doubt here also. So let me, okay, so this is the 3-level quantizer we have. Okay, so for this, let's try to sketch the quantization noise. So here. So let's say this is 1/4. This is minus 1/4. Okay. So if I plot, if I plot the quantization error or the negative of the quantization error, where I take the difference between this straight line and this step curve, what do I get? So in this range, you find that the quantizer output is 0, but the input is increasing. So the input minus the output will also increase. Let me draw it like this. Fine. Because here the output is 0, right? But the input is still increasing. So quantization error will also increase. And at this point, we have a sudden jump, right? So, and the jump happens when the input crosses 1/4. When the input was just below 1/4, the quantizer output was 0. So the quantization error would be 1/4 here. Okay. And the moment it exceeds 1/4, the output goes to half. So the quantization error will again roll back to minus 1/4. Right? Is that fine? So at this point again, the quantization error will become 0. Okay. So let me draw that here. So at this point, let me slightly push it away. Say this is 1. So at this point, what do you think is the quantization error? Sorry, half, right? Because I mean, this is output is 1, but the input is 1, right? So the quantization error can, I'll draw it slightly better. Okay, so this can go to half, right? Similarly, at this end, it will go to minus half. Okay. So now you find that the quantization error, even if there is some mistakes in the threshold voltages like this, right? So ideally, you want the decision levels to be at these points. Okay. And if that is the case, you find the quantization error here is bounded between plus or minus 1/4 and maximum is plus or minus half. So if you use a gain of 2, the error still remains within the limit, right? So now let us say there is an error in the comparator decision levels. So let's say I'll consider only at this point. So now what will happen? The quantization error will also grow till this point. Fine. And then it will do something like this. Okay. So now the quantization error is beyond 1/4, but it is still less than 1/2. Right. I mean, I'm assuming a small error, right? So the quantization error is here is still greater than 1/4. But as long as it is less than 1/2, if you use a gain of 2, we are not going to saturate the next ADC. Is that clear? Okay. So I think one of you had asked this question, right? So here the quantization error is going to plus or minus half. But that is okay because if you use a gain of 2, this is still within plus or minus VREFs. Our original goal was that if there is any error in the comparator threshold voltages, we want to make sure that even in that case scenario, amplified quantization noise stays within the bound, right? So here, if there is any error in the comparator threshold, the quantization error is just above 1/4, right? So if you use a gain of 2, it's going to be slightly greater than 1/2, and that is still okay. Okay. And in this case, can you tell me what is the maximum error you can tolerate in this error? That is this guy. What is the maximum error you can tolerate? So, sorry? 1/4. Is that fine? Is that clear to everyone? Right? I mean, because you want this error to not exceed 1/2. Right? This is our limit. We are using a gain of 2. So the even if with any kind of comparator decision errors, we want the quantization noise to be within plus or minus 1/2. Right? So we can afford to have a scenario like this, right? Where the no, if you have half, what will happen? This is 1/4. This will become 3/4, right? I mean 1/4. I mean this point is 1/4. So if you are saying if you can, let's say you make an error of half, which means the error or this decision point moves to 3/4. right? So if we have a 3/4, this will exceed beyond 1/2. Correct. That's all. The point is this error you can make in the comparator decision point, that is this error. In this case, it's 1/4. Okay. Or like if you want to be clear, it's VRF by 4. So you can tolerate this much error, right? Okay. And of course, we saw since we have only 3 levels, it corresponds to a resolution of log to the base 2 3. That's roughly 1.5 bits. So this is often called the 1.5 bit ADC or 1.5 bit stage. Okay. So the bottom line is here again you see that we have a redundant level, right? And this additional level we are adding because we want to tolerate any kind of mismatch in the comparator threshold, right? So the summary is, if you want to tolerate any kind of non-idealities in the ADCs, the way to go is have a redundant level or have a redundant bit, right? So you have more number of levels so that you can tolerate errors in the ADCs. That's all. That's how we tackle it. No, instead of designing a quantizer like this, you design a quantizer like this. You have 3 decision levels. I mean, if you want to have a single bit quantizer, what you do? It's a simple comparator, right? So you give the input. If the input is greater than 0, it's 1. Less than 0, 0, done. So now you cannot simply have one quantizer, because how many decision levels are there here? 2, right? I mean, 3 output levels are there, but the decision you are making by comparing the input with these 2 levels. Okay. So you need to have 2 comparators here. One compares with minus VRF by 4, and one compares with plus VRF by 4. That's all. Again, the output is 2 bits, but it has information corresponding to only 3 levels. That's all. So here again, you see this. In principle, this is only 1.5 bits. We have 2 bits, so that additional is redundancy. That's all. That's fine. Any questions? Okay. So now let's move on to the error that we can make in other parts. So now we saw what happens when you have error here and how we can tackle this. Sorry? Correct? If we, no, even beyond that, we saw, right? So even in a 2-bit or a 4-level ADC, you can have mismatches here, and that can make the quantization noise grow beyond the bounds. And that is why we choose the gain to be of this form. I mean, the point is, if you have ADC with what? Correct. Yeah. Correct. Yeah, correct. Yeah, what he's saying is, if you have an ADC of 2 bits, you can obviously use a gain of 2 power 2 minus 1. That is 1. It's fine, right? Only if you have a 1-bit quantizer, you cannot follow that logic, because that makes the gain 1. So in that case, you have one more additional level. That's all. So now that we have seen what happens, errors, what happens when you have errors in the ADC. So let's correct.
But for implementation, we still differ.
Yeah.
Basically, even like when you also having
I mean, 1.5 bits is the effective resolution, so 2 bits. So you can say it's 0.5 bit of redundancy. I mean, the best way to think is in terms of the levels you are introducing, right? Earlier you had only 2 levels. Now you have one additional level. That's the way to think about it. Bits is something, I mean, that is not something you can directly calculate, right? The number of bits, it depends on the number of levels you have, right? All we talk about is the number of quantizer levels you have. That's all. Okay. So let's now see what errors you can have in this residue amplifier. So let me draw the Let me draw a two-stage pipeline ADC. So this is my first ADC, output of the first ADC. I'll take the difference, amplify it, and give it to the second ADC. So let's say this is some 2-bit ADC. What should be the gain you use here for having one redundant bit? 2. Fine. 2 power 2 minus 1, that is simply 2. So let's say this is again some 3-bit ADC or something. So what are the non-idealities you think this amplifier might have? Okay, gain error and offset. Okay. So one thing is obviously you think that you are realizing an amplifier with a gain of 2, but in practice nothing is going to be as you wanted. Something, I mean, there will be a lot of things that is going to destroy your design, right? And you will not get an exact gain of 2. So, and the other is, of course, you will have an offset corresponding, I mean, associated with the amplifier. First, let's discuss the offset issue. So let's say this has an offset here. Okay, this is the offset of the amplifier. Okay. So what do you think will happen at the output? Okay, can you tell me what is the output of the first ADC? If let us say the input is U, this is quantization error Q1 and Q2. Yeah, sorry. Fine. What will be the output of the second ADC? Fine. It's minus G times. Sorry, minus G times. Fine, no? Q1 plus POS. Okay. I mean, this is just minus Q1, you're adding offset to it. So Q1 plus POS is amplified. So this is the input, right? Plus the quantization noise. Yeah, plus Q2. So again, as usual, you combine the output in this form, B1 plus B2 by G. So what do you get at the output? I'll obviously have this guy. I better get this because this is what I want. So what will be the additional term due to the offset? Sorry? Minus POS, right? I just say some plus or minus POS because I'll say everything is plus or minus. Okay. Yeah, is that what I right? Fine, no? I mean, the input here is correct, right? Or did I make a mistake here? This is minus Q1. Right. Correct. Oh, okay, okay, sorry. Okay. This one, right? Is that what you told? Yeah, okay. So this is minus Q1. Yeah, that's good. Fine. No, I'm saying it's plus or minus POS. Don't worry about offset's polarity. Offset can be plus or minus, so I'm not worried about it. Okay. So this is the thing you get. So you find that if you have an offset in the first amplifier here, that obviously directly adds to the input, right? Because it's like you're adding the input to the offset directly. Sort of thing. Okay. And but one thing you should be careful is the input to the second ADC here. What is that? That is minus G times. Sorry, I made a mistake. Right? Yeah, this is what you are saying, right? So G times minus Q1, some plus or minus POS, right? So now, as usual, we want the input here to be within plus or minus VREF, right? Now, although we have chosen a gain to be less than 2, we need to make sure that this offset is not so high that the input here is exceeding plus or minus VREF. Okay, so that's the only thing we need to take care of here. Fine. So yeah, so amplifier offset here just acts as an offset to the overall ADC, and in many cases this might be okay. And the only thing that needs to be taken care of here is make sure that the offset is not so high that it saturates the succeeding ADC. That's all. So now let us say we have a 3-step or a 3-stage ADC. So let me quickly draw that. Oops. So let's say now this second amplifier has an offset. Say it's VOS2. Okay, so let's say this is G2 and G1. So V1, V2, V3. Okay. So what do you think will happen here? I mean, you saw that an offset here that was directly appearing at the input, right? So intuitively, can you say what will happen if you have an offset here? If I refer it back to the correct, but let's say I want to refer it to the input here. That's fine. I mean, you can simply write the equations for V1, V2, V3 and find out. But the idea is here you have an offset here. If I want to refer it back to the input, VOS by G1. Okay. So the point to note is that the offset of the succeeding ADCs or the succeeding amplifiers, they are getting divided by the gains. Okay. So the important thing to design for is offset of this guy. Right. So besides that, there is nothing serious to it. So let's now focus on the gain error. So let me just take the two-step case, for example. Right. So let's say ideally you want a gain of G1, but let's say you have realized a gain of G1A and just writing A because it's analog gain, right? So I'm saying it's G1A. So this is the value that you want ideally, right? And let's say you have V1, V2. So ideally you want analog gain to be G1. And even when you combine the output, V1 plus V2 by, you'll have a digital gain here, right? So this is some, let's say G1D. You want this to be equal to the digital gain also, right? But in practice, this analog gain will not be equal to G1, right? Can you say what will, I mean, can you comment on G1D, the digital gain? I mean, let's say I want to realize a gain of 2 power B. Do you think, will there be an error in this realization or no? No, yes, no? No, right? Because I mean, dividing by 2 is simply right shifting, right? See, the moment you right shift is exactly divided by 2. There is no error that you can introduce in the digital gain. Fine. The only gain that you can have is in the analog. So let's see what happens now. So V1 is Q plus Q1. Fine. V2 is the input at this point. So this here is minus Q1. So this should be minus G1A times Q1, right? So this is minus G1A times Q1, the input, plus the quantization noise, that is V2, divided by the digital gain. I'll just write as G1 because we can exactly realize the required gain in the digital domain, right? So what happens here? I obviously have U plus Q2 by G1. Plus I'm getting something. What is it? Q1 times? Yeah. So what exactly it is? Q1 times? Fine. So now you see that if you have a mismatch or an error in the gain you use here, the quantization noise of the ADC is not completely getting cancelled. And some of it leaks to the output, right? So in some cases where the gain is very close to G1, this guy might not be so high. That is, this fellow might be less than Q2 by G1. So it might still be okay, right? But in many cases, if you have, or in some cases where the gain is much away from or is so different from the required gain of G1, then this guy might be comparable to Q2 by G1, or it can even be higher, and it will kill the overall resolution of the ADC. Sorry, why we? Okay. The gain you realize here must be in the analog domain, right? Because the input is an analog signal, right? And of course, here I have a DAC. I didn't write it, right? So this is an analog signal. So which means the you need to have an amplifier here that amplifies the analog signal. Whereas when you recombine the outputs, these are all digital bits. So there you have a digital gain, right? Okay. So the point is, in some cases where you have the analog gain to be close enough to G1, this leaked quantization noise might not be so high. It might be lesser than this quantization noise itself. So it might be okay. You don't have to do anything. But in some cases, it might turn out that there is a huge error here, and that will kill the overall resolution. Okay. Any doubt? Can you repeat again? How do you do that? Yeah, how do you cancel this fellow? Yeah. I mean, this is equal to this, right? But the point is, Q1, Q2 are not, what do you say, related, right? They are unknown and they are not even related, right? They are completely uncorrelated. I mean, if this was the same signal, then you can easily do it. If Q1 is equal to Q2, then you can easily do it, right? Now, these are all some random signals that depend on the input you give. Okay, you might be able to cancel it at 1 or 2 time instance, but for all time instance, you cannot do it. Okay, so let's stop here and we'll see what can be done to correct it in the next class.